So let's start with this third lecture. Welcome to the late universe. Okay. So today, as I promised yesterday, in this lecture we will try to address the remaining questions, open question in cosmology. Okay. Of course, these are personal interpretation of different aspects of the universe, of cosmology, that we try to address with different probes, and in particular, in my case, in our case, in the collaborations, so using gravitational waves. So since, as I was saying yesterday, we realized that gravitational waves can really help us to understand the early universe. Today, I want to show also what happens in the late universe. So when I talk about late universe, I mean small redshift. We will see what this means, okay? And what are the horizon of second generation detectors like LIGO, Virgo, and Kagra, and the horizon of next generation detectors like ET, LISA, and so on, okay? So these are the questions that I will try to address if I have time, okay? I will start from mainly some things that has become very popular in the last year, that are cosmic tension, and in particular the H-naught tension, okay? I will introduce you to the topic and try to tell you why this has become a so interesting topic, okay? And in the final part of the lecture, I will also give you some hints of on how to use gravitational waves to test the actual acceleration of the universe, okay? With respect to yesterday, so these two questions, or these two open questions, can be addressed using resolved sources of gravitational waves. Yesterday, I introduced you to the stochastic background. Forget about that, okay? And let's move to the resolved sources, okay? Well described by our waveform, okay? That Costantino will discuss more in detail, okay? But let's take these resolved sources and let's understand what they can tell us about the late universe. So this is the outline of the lecture, okay? I will show you how to perform what is called cosmography with gravitational waves. So I will show you, will introduce you the likelihood for the different technique to perform inference of cosmological parameters, okay? And then, as I was saying before, so I will talk about dark energy and modified gravity, okay? So as yesterday, so let me give you some references, okay? So the first references are some of the first paper or review where there is the discussion about the likelihood and the kind of likelihood that we will see in the lecture. And then here you will see more the final, this last references discuss more how to perform the inference of cosmological parameters, okay? So let's start, okay? So I think let's start with a bit of history. So in the history, I think begins in the 1920, okay? When this guy here, Edwin Hubble, discovered that the universe was expanding, okay? He was looking to the distance of the nearest galaxies, okay, using the CFITs, okay, and he realized that the galaxy redshift was proportional to the distance, okay. So more this recession velocity increase, more distant are these galaxies, higher is the velocity of these galaxies, okay? So, and this is a clear indication that there is a relation, that there was a relation between these two quantities, okay? And so since this happens 5 years later than Einstein prediction or Einstein description of general relativity, okay, where we were understanding that the universe was expanding, okay, people realized quite soon that there was a relation between the expansion of the universe and these redshift that stretch the wave, the light, if you want, to longer wavelengths, okay? So, and let's understand where and how, so today, we extract distances from astronomical or astrophysical object, okay? It depends mainly from the distance that we are looking at, okay? So let's say that up to the parsec scale, So we call this, or up to the kiloparsec scales, we typically use astronomical determination of distances, and in particular at very small scales around the solar system. So we use typically radio frequency, okay? We send the radio frequency pulse, we expect that it comes back, and then we measure the time, and then we have a determination of the distance. Moving further, so we typically use the apparent motion, apparent position of the stars, okay, or a body in two different positions of their orbits, and then we measure the so-called parallax, okay? And this typically allows us to determine distance around 100 of parsec, okay? Then if we move to larger scale, so towards cosmological scales, so we start relying on some photometric measurement that allow us through the distance modulus, so through the magnitude, to extract information about the distance of this object, okay? And then here, so it means that we are on the Milky Way, let's say, sides, okay? So then if we start going further, so we start to focus on nearby galaxies like Andromeda and so on and so forth, so you start employing the use of CFITs that are very well-known objects to which we know very well the luminosity, okay? So, and then we rely on this relation between the luminosity and the period that allow us to extract again the distance of these nearby galaxies, okay? So, and finally, if we move on megaparsec scales, where galaxy clusters start to appear, okay? Again, we use the Tully-Fisher relation typically, and again, this relation between the rotational velocity of this guy and the absolute luminosity, again, we extract the distance modulus, and we get these distances, okay? So then if we move further, okay, it starts to be very interesting, okay? Because at further distance, at gigaparsec scale, okay, cosmological scale, so we rely on the Hubble law, okay? And moreover, moving forward, okay? So we rely on a standard technique that we usually call early universe probes, because these are BAO, baryonic acoustic oscillation, and the cosmic microwave background to determine the distance of the object, okay? And in particular, more than the distance, the Hubble parameter, okay? So in this case, so we use the fact that photons and baryons in the early universe, they are highly coupled, okay, tightly coupled, okay, sorry. So, and then, so at some point the photons decouple, okay, and this happens at the sound horizon, at the recombination that is around 150 megaparsec, okay. This is a very standard ruler, a very precise standard ruler, and using this sound horizon, we are able to determine the distance through BAO, that are these imprints of this sound horizon on our galaxies, and similarly, also looking at the peak of the CMB in the angular spectrum, okay? Again, so this is the CL, okay? This is L. So it's not, for H naught, it's not just one peak, okay, that determine H naught. It's a combination of the position of the peak, okay, and also of the height of the peak, okay. So it's in both directions because it's degenerate with other cosmological parameters. So here is a full list of all the distance or determination for which we can extract information on the Hubble parameter, okay. So, but what happens in the recent year, okay? It happens that if you look at the distance ladder, or I would say late universe distance ladder, and you compare with the early universe ladder, or the early universe determination of the Hubble parameters, it starts to appear that the measurements are in tension, okay? So you see, on this side here, on this line here, and in particular on this first part of the plot, you see all the determination of H naught using CMB measurement, okay? While in this part here, okay, you see all the determination done that we have discussed so far. So CFITs, the tip of the red giant branch that I didn't discuss, but So you can find information in the reference that I give you, and also all these methods. So, and if you see, the measurement from indirect measurement through CMB does not agree with the measurement from standard candles, okay? The one that we have discussed so far. And you see there is a kind of 5 sigma tension, okay, between this low and high redshift measurement of the Hubble parameters. So then the question is, what is there? Is systematics, is new physics, is something else? And people are trying to address this question, and you see that in the recent year, the amount of people working on the so-called Hubble tension is increasing very fast, okay? Because really there is a lot of interesting physics to understand, and we are trying to understand if gravitational waves can be useful in this job, okay? So we are trying to see if they can tell something more compared to CMB, determination, and the cosmic distance ladder. Please. Very good. So I will discuss more in detail, okay, in the next slide, where I will discuss more. So the let's say the late universe determination, because you know all this distance ladder here must be calibrated, okay. So, and the calibration in reality is even more difficult because each of these ladder rely on a calibration that happens from the previous one, okay. And there is a lot of uncertainties. So, for instance, in the astrophysics of CFIDs, that today are the most famous ladder and most reliable, together with supernova, to extract these distances that relied on many astrophysical assumptions, okay. So, if you talk with the pure astrophysicists, they say that we are underestimating a lot of astrophysical uncertainties in this determination of the distance from astrophysical object. So in reality, CMB is linear, guys, linear things, okay? So it's true that there could be some effects also in the CMB determination, but this is a personal feeling. This is linear physics that we have quite under control. And we have, as you can see here, so very stringent measurement with very small error bar, okay, that points towards this determination. Here you see they have not been distinguished, the two, but you see that there are both astrophysical and systematics uncertainties. Yeah, sure. Yeah. So there are mainly, that as far as I know, two groups. There is the group by Adam Rees, and then the group of the Wendy Friedman. So these are the main two groups that are looking at this different determination, the Schultz collaboration and the Wendy collaboration. So they are looking at all these kind of uncertainties, yeah, the determination. Yeah. Okay. So I will not discuss this because I will need the next lecture in the next school, okay? But I absolutely agree with you. There has been a lot of proposal, okay, to try to reconcile these two measurements. I will not discuss these. Let's say that they are going in these three questions, okay? Absolutely, I agree. There are many proposals to try to reduce. But the proposal that I like more is using gravitational waves, okay? Okay, very good. So, but let's try to understand how we can extract distances from gravitational waves, okay? So we are lucky, so we live in an homogeneous and isotropic universe. We have our Friedman-Lemaitre-Robertson-Walker matrix. This simplifies a lot our life, okay? So, but our universe is expanding. So we have to keep, let's say, an eye on the fact that in an expanding universe, there are physical distances and comoving distances, okay? So these comoving distances are distances that they remain fixed, okay, with the expansion of the universe, okay? Forgetting about peculiar velocity and so on and so forth, okay? So local distortion, let's say. So let's try to understand how these are related, okay? So we put ourselves in a simplified situation where we have a flat universe, okay? So, and we forget about, we just consider the radial distances, okay? And from this metric here, you easily get a relation between this term here and this term here, okay? And you see, there is some things that remember us that we are living in an expanding universe. If we integrate this quantity, okay, you integrate on the left-hand side and on the right-hand side, okay, and you see that there is a simple relation between the physical distance and the comoving distance. And what happens is that the scale factor, okay, is the guy that relates these two distances, okay? So remember, this keeps fixed on objects that move with the expansion of our universe. Instead, this fills the expansion of the universe, okay? Okay, very good. So let's try to see then why, so these galaxies, okay, are faster, move faster when they are far away, okay? You take this relation, very simple, you derive this relation in time, okay? And then you see that you have the derivative of the scale factor, okay? And you have also this term that is the derivative of the comoving distance, okay? So, but I told you that this guy is comoving, so it's fixed, okay? So this term is 0, okay? This is okay for faraway galaxies. And then you see, you find a simple relation between the variation in time of the physical distances and the Hubble parameter, okay? You see that there is this relation, okay? This relation, I didn't find it, so Hubble find it, okay? And this is the famous Hubble law, okay? It describes essentially that in an expanding universe, the cosmological object, like galaxies, for instance, they run away from each other with a velocity, d prime, okay, that is proportional to their distance, okay? So, and in reality, this relation was found already in the 1930, okay, where Hubble, observing the relation between the velocity and the distance relation and the distance between extragalactic nebula, he found that there is this linear relation, okay? So if we are at small distances, okay, very close to us, this Hubble guy, okay, this Hubble parameter is constant, okay? The relation is very simple. Recession velocity is proportional to the distance through a factor that keeps into account that we are living in an evolving universe, okay? Remember that this holds at small distances, okay? When we go to higher distances, we have to keep into account that our universe is full of matter and is full of dark energy, okay? So this relation will be modified, okay? So, okay, good. So we understood how the recessional velocity is related to the distance. Then the next important quantity to introduce in cosmology, okay, is the redshift, okay? So, and the relation that is between the redshift and the so-called scale factor, okay? So the relation is very easy, okay? You see that you can write your scale factor at the emission time like 1 plus 1 over z, okay? So if you determine the redshift, okay, you can get information on A, okay? And this, okay, is telling us that if we want to measure the cosmic expansion from individual sources, so we need to measure the distance of the object and the recessional velocity, okay? Very good. So, and here you see that the recessional velocity is equivalent to the redshift. Okay, great. So we have all the information that we need. So, and since we are living in this evolving universe, okay, this distance changes, okay? We understood this. So the fact that this distance changes is related, if you want, to the fact that if we would live in a static universe, Euclidean universe, okay, this flux is related to the luminosity, as you know, through the square of the distances, okay? So in the full, let's say, 3D circle, okay, on the sphere. Unfortunately, no, not unfortunately, fortunately, so we have to keep into account that the universe expands. So this relation modified because the energy of the photons is redshifted by a factor 1 plus z, and also the rate at which photons are emitted is redshifted by a factor 1 plus z. So you have to keep into account these, okay, in your flux that you are receiving, and you see that the luminosity is scaled as the square of the moving distance times a factor proportional to 1 plus z square, okay? So this means that if we know the intrinsic luminosity of an object, okay, then we can measure its luminosity distance. And it comes out that there is this useful relation that relates the co-moving distance, okay, to the luminosity distance. And this quantity here, so will be very important for gravitational waves. Okay, any questions? Yes. Because you have, it's written here, so each photons, okay, is redshifted, okay, and also the rates at which photons are received have another extra factor of 1 plus z. So, exactly, exactly. So great. So we have this distance, luminosity distance, co-moving distance relation, okay? And let's understand what are the problems that Gianluca was mentioning, okay? So standard candles are not self-calibrating object, okay? So we are looking for something that is self-calibrating, that does not rely on a calibration of another distance ladder, okay? So, and of course, this indetermination is propagating when you do this calibration, okay? The other problem is that the intrinsic luminosity needs to be calibrated on closer standard candles, okay? But this introduces systematics in the calibration again, okay? So not all the ladder that I present you are reliable. The only ones, the ones that are more reliable are CFIDs and supernova type A1, okay? That are so-called standardizable, okay? And then there is also the tip of the red giant branch that I will not discuss. So these rely on relatively nearby galaxies, order of a few megaparsec, okay? And then typically, I didn't explain you in details, but the way in which we calibrate or they calibrate is through the magnitude color diagram, okay? And this, in this case, so you know, it's very sensible to evolution with redshift and also with the host galaxies properties, okay? So, and then there is a problem of the Malmquist bias, okay, that require to take into account the fact that we have selection effects that refers to the fact that we observe a kind of object, but we don't observe other kind of object, okay? And these are some alternative methods that I will not discuss in this lecture, okay? Okay, good. So we found this simple relation between the luminosity distance and the co-moving distance, but so we didn't introduce the fact that when we go at higher redshift, as I was saying, so the universe is filled by matter and dark energy. I neglect here the radiation domination because it's a negligible contribution, okay? But if you take your Friedman equation and you compute your Hubble parameter square, so this is essentially your Hubble parameters, you see that the first Friedman equation is telling us that there is a relation between the Hubble parameters and some other cosmological parameter, okay? So this means that if I move to higher redshift, okay, I need to modify my relation, and you see here that the luminosity distance is equal to this quantity here that keeps into account the amount of matter and dark energy that is in our universe, okay? So this becomes absolutely necessary when we have a further object, as we will see, like in the case of GW150521, or for third generation detector, as we will see. Okay, good. So this is the introduction, okay? And I think that all the information that I give you, you already know. Now let's try to understand how this universe evolution change the waveform of the gravitational waves. Because of course, the waveform and the evolution of gravitational waves, they feel the evolution of the universe, okay? So I think that the waveform, okay, in Fourier space, in the post-Newtonian expansion, has been already introduced by Cliff, okay? So don't need to explain much, just to tell you that these are characterized by an amplitude and by a phase. But keep an eye on the fact that this waveform, at least here we are not accounting yet for the universe evolution, has inside a couple of relation with the physical distances and Chirp mass, okay? Keep remember this. And here you see the definition of the Chirp mass that is related to the mass of the two objects, okay? So what happens if we include the fact that the universe is expanding, okay? Of course, the frequency is redshifted, And I have to consider that I'm detecting my gravitational waves in the detector frame. D means the detector frame. But this waveform emerge from the sources, okay? So there must be a relation between these two that takes into account the universe evolution, okay? But there is a very simple understanding of this that is essentially the fact that when you measure stuff at the detector, the signal is equal to the signal detector for the signal, original signal, but the only things that you have to do, you have multiplied by redshift factor and computed frequencies that are redshifted, okay? The relation is very simple. So here I am in time domain. You have to work out this frequency in the frequency domain, this waveform in the frequency domain, but the math is very simple. So if you do the job, so you realize that the phase change in this way, okay? There is the introduction of the redshift, okay? For the frequency, for the time, and for the chirp mass, okay? One thing that I want to stress is this relation here. So you see the mass, the chirp mass in the detector frame is related to the chirp mass in the source frame multiplied by a redshift factor, okay? So keep remember this relation because this is crucial for the determination of distances using gravitational waves. Great. So all the information are kept. So we can extract information on the sources, okay? But we must be very precise, because we have to know precisely the redshift of these sources in order to relate this quantity from the source frame to the detector frame. So of course also the amplitude changes, okay? So, and you see the physical distances now is multiplied by a factor 1 plus z squared, okay? So we are keeping inside the fact that the universe is expanding. So the full waveform in the detector frame, okay, are these, okay? These are the most simple waveform, okay? So if you want more details, ask Cliff, okay? For us, this is enough, okay? So the only things that you have to remember are these two simple relations. The fact that the physical distances now has become a luminosity distance, okay? And the chirp mass in the detector frame is the chirp mass in the source frame multiplied by a factor 1 plus z, okay? Remember this, so the waveforms maintain the same functional form, so you just replace these two relations and you have your quantity in the detector frame. Okay, very good, okay? What we have learned, okay? We have learned a couple of things, okay? That from the waveform, so if you have this guy, you can measure, so if you measure gravitational waves, both the chirp mass and the luminosity distance, okay? So, very good, okay? So, there is one point that I stressed before, okay, that the chirp mass, okay, are degenerate with redshift, okay? I cannot disentangle the redshift from the mass based on the waveform alone. So, if I measure the waveform, the fact that there is this relation here does not allow me to disentangle if the effects come from the redshift or from the mass, okay? So this means that I need a way to understand, to break, if you want, this degeneracy, okay? But there is a very nice point with respect to the standard candles, or the object that I have discussed at the beginning, that is that the CBC, the compact binary system, okay, can give us directly the distance via the gravitational wave emission without relying on any other external calibration, okay? So I don't need to calibrate on other ladder. They are self-calibrating object, okay? In contrast to electromagnetic sources, okay? So if you measure gravitational waves, you soon know what is the luminosity distance, with some uncertainties, but you know, okay? So these help us to break what Gianluca was discussing, all these astrophysical uncertainties, okay? To alleviate at least. But there are other problems. So then the question is, then how I get the redshift, okay? So I have all this information. This is the summary that is here from all the previous slides. So I measure the gravitational waves sourced by the merging of two objects. I measure the detector mass and I measure the luminosity distance. Great. So this allows me to directly infer the distances, okay, without relying on any calibration. So now you have to give me the redshift, and I can control our universe, okay? How do I determine my redshift? Who has idea? That's a kind of method that we will discuss. Nice answer. Okay, but sky localization, how do you do? I imagine that I have black holes. How do you see? What is it? Eh? Okay, you want to play safe. Other question, other suggestion. You also play safe. Someone that is more brave. Masses. That's a very brave answer. How? Okay. Okay, good. So essentially, you know all the methods that we use, okay, already. So I don't need to explain. But so the three methods that are standardized in cosmography are these three that essentially you described already. So, and they are the bright silence method. What people were mentioning, multi-messenger, is that you have your gravitational waves event. So you are lucky because one time in 10 years it happens that this come out with an electromagnetic counterpart that allows you to shrink the determination of the position of the gravitational waves simultaneously, okay? And this gives you a very precise determination from electromagnetic probe of the position of the black holes. But unfortunately, we have one event of this in 10 years, okay? So we cannot rely on only one event, as we will see. So, but we have many more events of binary black holes, okay? In this case, except in some cases, so we don't expect any electromagnetic counterpart, okay? So this means that we have to rely on the fact that this guy are in galaxies, okay? So, and we can do a statistical association of the position of the black holes with the galaxies that are around, okay? So I will explain you better all the three methods, okay? And the final method is what your colleague was mentioning. So I measure masses in the detector frame, I measure masses in the source frame. So I explain you that the two are related, okay? You assume a mass distribution for your events, and you kind of breaks this degeneracy that allows you to get the redshift, okay? So these are the main three methods. Then there are others that I will not discuss that are, for instance, the love silence method that rely on the tidal deformability of binary neutron stars, or some method that does not work in redshift space, but they work in the angular domain and they use the cross correlation between galaxies and gravitational waves that I will also not discuss here. So remember these three methods and let's go through them, okay? So let's start from the bright silence because it's, how to say, very powerful, I would say. So as your colleague was saying, we like to play safe, okay? So, and we like to rely on a merger of neutron stars and black holes, neutron stars alone or black holes and neutron stars, okay? So I measure the gravitational wave signal. This comes from the spiral and the merger waveform, and you measure your luminosity distance. So we have seen that in the waveform, we have the luminosity distance. At the same time, or a few seconds later, it happens that in the same position in the sky, or close to that, there are some electromagnetic counterparts. People much more expert than me have realized that the three main contributions from the electromagnetic spectrum comes from gamma ray burst, okay? Then we will comment on the short, okay? And then from kilonova and from afterglow emission. And here you see a snapshot of the kind of ejecta that you would expect from emerging of two neutron stars and the relative electromagnetic emission, okay? Okay, very good. So I have the black holes, I have the two neutron stars that are merging. I have the electromagnetic counterpart, what I learned, okay? So the nice thing is that the information that the gravitational waves and the electromagnetic sources bring, okay, are absolutely complementary. So I measure the waveform and I extract mass, spin, systematic orientation, luminosity distance, and the binary rate, okay? I call my friends on the astronomical facilities and I say, look at there, okay? And they give me the precision at the arc-second level of the sky localization. That is wonderful for what I want to do. They give me, fortunately, the host galaxies. They give me the redshift, and this is very important. And then they give me also astrophysical properties. Wonderful. Let's combine them. And what happens is that 8 years ago, 1708-17, okay, in the 2017, these events happen for true, okay? So at Advanced LIGO and Advanced MIRGO made the first observation and at the moment the only confirmed observation of a binary neutron star in spiral merger, okay? So you see here the measure in the spectrogram, the signal measured by Hanford, Livingstone, and Virgo, okay? And the most beautiful things was that these events arrived a few minutes later, a few seconds later, with an electromagnetic counterpart. You see here that the GBM, both the integral detector on Fermi and also the GBM, detected some emission of gamma ray, okay, few seconds later, okay? And also, there was later, or the day later, if I remember well, also some optical observation, okay? Good, so I have a gravitational wave detection together, a few seconds later, here with an electromagnetic counterpart, okay? This was a GRB, the so-called GRB 1708-17A, okay? That was individually detected by Fermi GBM and the integral, okay? 1708-17 was the beginning of the multi-messenger astronomy. Okay, so this was the first events that allow us to have both the gravitational waves and an electromagnetic counterpart detection. Okay, so then people work a lot more on this, and they realized that this was a short GRB. Okay, measuring the T90. Okay, so but the astrophysical, cosmological, and fundamental physics and cosmological implication from this event was huge. Okay, was really huge, and we learned many things. Okay, I just focus on what we learned for cosmology. Okay, I don't discuss what we learned for fundamental physics, as Costantino will discuss. What we learned from astrophysics, that probably Zoltman has discussed. Okay, so we learned something very useful. That was the first determination of the Hubble constant using gravitational waves. Okay, so you see, we will discuss more in detail this posterior distribution here. But just to tell you that there is a gravitational wave posterior in the middle between CMB detection measurement and cosmic distance ladder from supernova measurement, okay? We will discuss this more in detail later. So we have tested deviation from GR. So the fact that this gravitational wave signal and the electromagnetic signal happens almost simultaneously allow us to estimate the velocity of the gravitational waves, okay? And we realize that the gravitational waves travel at the same speed of light. So you see there is a difference of order 10 to minus 16. Okay, if you have measured the velocity, you learn also about the mass. So you look at the dispersion relation and you put the most stringent bound on the mass of the gravitons that is of order 10 to minus 23, okay? So these are great implication for fundamental physics, but also for cosmology and in particular for modified gravity. Because what happens is that up to 2017, people were working a lot trying to substitute the cosmological constant with some alternative models that are modified gravity models. In all this is not exhaustive, this list. These are just the models that were mainly constrained after 1708-17. So you see, there were many models that were providing a velocity of the gravitational waves equal to the speed of light. But there are a lot of models relying on modified gravity that were implying that the gravitational waves propagation is different from the speed of light. And of course, with this stringent test, you can cut all the models that are in these red boxes, okay? So then what happens is that modified gravity went down a lot, and people lose a lot of momentum in trying to propose alternative models of modified gravity to explain dark energy, okay? So this slide summarizes what we have learned, okay? But this is not only things that we have learned, and I will try to tell you now what we will learn with the future detection of gravitational waves in cosmology. Okay? So since you mentioned, I want to explain also this, okay? That is the model that probably has more statistics, okay? So in some way it's more difficult, but it's true that having more statistics is the one that we can rely also, okay? So as you know, the main the main problem related to the determination is that in the position space where these gravitational waves events happens, there are many galaxies. Okay, so I need to find a way to associate to which galaxies these gravitational waves is related. Okay, so I can only rely on statistics. Okay, and the technique is the following. I look in a particular direction where the gravitational waves events happens, okay? So I have my gravitational waves data, so I know that there are many galaxies, okay? I look at the probability distribution of these galaxies and I combine the two, okay? I combine these two probability distribution and I obtain, okay, from the redshift and from the luminosity distance, a posterior distribution for H naught, okay? I just measure this, and I make inference on the parameters that I don't know. Okay, great. So another event, since we have one event per week, okay, at the moment. So I look in another direction and I play the same trick, okay? Again, you see, I extract another posterior distribution for H naught, okay, and so on and so forth. So since I have almost 200 events, okay, you can combine all of them, and what you obtain are many posterior distribution for H naught. Okay, so then you take your posterior distribution, you combine them, and you obtain a posterior distribution for a joint posterior distribution for H naught. Okay, the life is not so easy, as I draw in this cartoon, and we will see why. Okay. So there has been events that are very well localized, okay, and you can understand that if you reduce this posterior distribution, then you obtain very powerful constraint on cosmology. And 1908-14 was one of these events where you see that the localization error is very small, okay? It says 88, 90,000 megaparsec cube, okay? But the things that I want to stress is that the galaxy survey are another way to obtain the redshift determination, okay? And finally, okay, let's discuss some things that was mentioned, okay? So, yes, please. Yes, yes. We will see better when I show you the likelihood, okay, how it works. Okay, very good. Any question? Any other questions? Yeah. Yes, we will see in the likelihood how I combine them. Yeah. It's the opposite. I look where the gravitational waves comes from, okay? I see statistical, I identify at 1 sigma, 2 sigma, and 3 sigma all the galaxies that are around these gravitational waves events, and then from these I extract my posterior distribution and I combine them. Yeah, I want to measure them independently. Mm-hmm. Yes. Yep. Yes, there are works on that by Rachel Gray mainly that is putting this prior determination on the galaxies. Okay, so I'm not going to discuss because it's a bit technical as a point, but there is this line of sight prior. Okay, so there are these, as you were saying, this way to put some prior on the fact that we know some properties of the galaxies and some information on the luminosity distance. Yes. No, not really. Okay. And I will tell you why. Other question? Because it's written here, okay? So we have a huge problem in this determination that is the completeness of the galaxy catalog, okay? So I was planning not to discuss this because this is a very, very, very delicate point, okay? But you have to remember, okay, that you have your galaxy catalog like in LVK that they use Glade Plus or Upglade, okay? So you have many galaxies, okay? But you see how much is complete? It's 20% completeness. So if you apply different completeness cut, as we will see later, this posterior change a lot. So they are very, very sensible, okay, to the completeness. Okay, and moreover, something that I also didn't discuss, okay, is the selection bias. So I will introduce briefly, but the fact that we observe a kind of sources, but we don't observe other sources, or the fact that my detector is limited, also impacts a lot this determination. Okay, so there are ways to address these kind of points, but so these are more technical. I was not planning because really it needs to take 1 hour to discuss this. Remember that this posterior and the fact that so we can marginalize is not easy because my catalog is not complete. So when I perform the marginalization, so I have to keep into account the selection bias. So it's not easy. Okay, so there was your colleague that was suggesting something very smart. Okay, that is the fact that if I have some information on the mass population, on of the mass distribution of my object, so okay, this impacts a lot on the H0 inference, and can be used, since I measure masses in the detector frame and in the source frame, to break this degeneracy between the mass and the redshift, okay? So you see, with the data from the GWTC3 and the previous catalog, so different mass distribution has been proposed, okay? The truncated mass distribution, a broken power law, a power law plus peak, and also a multi-peak, okay? So now, what happens is the following. So I told you at the beginning that the mass in the detector frame is related to the mass in the source frame by a redshift factor. This redshift factor depends on the L, depends on H0. So this means that if I measure the masses, okay, and I use this relation, okay, I can put this relation here. I see the mass distribution, how this object distributes in this plane, okay, and this helped me to break the relation. Okay, and this means that if there are some mass where black holes preferentially sits, okay, this can be used to infer H0. And let's see why, and let's see how, okay. Let's look at this distribution again, and let's try to fit this distribution with three models, cosmological models. So you see here, H0 equal to 68, H0 equal to 20, and H0 equal to 120. Okay, these are extreme value, but are really telling you that there are models that extreme cosmologies that don't fit the overdensity of binary black holes. Okay, so and this is another way that has been applied in the three runs of LIGO Virgo Cagra and will be applied also for 404. Okay. Of course, also this model has some troubles, okay? And let's see what are, okay? So, of course, this model relies on a perfect determination of the mass distribution, okay? that we don't have, because you see here from GWTC3, okay, that this posterior, okay, has some uncertainties, as you can imagine, okay. But in any case, so there are correlation, if you want, between the parameters. Here you see a posterior, you see a joint posterior for the one parameter that is characterizing the Gaussian peak. So let's focus for the moment on the power law plus peak model that has been used also here, okay? And let's look at this posterior distribution. You see, this is the peak of the Gaussian peak. This is the maximum mass, and this is a parameter that is related gamma to the star formation rate, okay, that Tanya was discussing yesterday. So you see, these parameters are correlated. So it's not clear, okay, and it's not easy to break the degeneracy, if you want, between population parameters that correlate with H naught, okay? So this is also a limitation of this galaxy, of these models, that, of course, needs to be taken into account. But there is a useful information for this method, or a useful application that does not rely on any catalog information, okay? So, and of course, all the points that we were discussing up to now, the completeness, the selection, okay, are a bit alleviated, okay? So, and this is a big improvement, and you can see that, of course, you can use also this method to infer H naught. Please. In this posterior distribution here. You see here, so these are the different posterior distribution, the power law, the broken, the truncated, and you assume that, for instance, this peak at 35 solar masses, okay, is the place where black hole preferentially sits, okay? So you see from here, so you see that this is the place where there is an excess of binary black holes, okay? You use this model in the posterior distribution, as we will see later, okay? Yes. You assume that. Because you see, you show here where they sit this guy, okay? So you see that in this case, for instance, let's look at here, okay? These are some example of the density of the masses for GWTC3, if I remember well, okay? So you see that there are two peaks in the two masses, and then you use this information here. You can use this information in this place. You look for some spectrum, because you look for some spectral, yeah, absolutely. That's true. You look for some features in the spectrum. If this would be a power law, you could not use this, right? Because it would be not informative, if you want. Absolutely. It can be much more informative, okay? And another point that I didn't discuss, that here I am neglecting the evolution with mass or with redshift. That can be another application, extensive application of this, okay? I'm saying that this mass at some point, as we will see, will not depend in some way on redshift, the intrinsic masses, okay? People claim that there could be a redshift dependence also there, okay? That is not only the dependence due to the expansion of the universe, but probably Michela will discuss, probably Mappelli, this mass relation, mass redshift relation. But I agree that if you change, so if we in the O4 run, this will change, okay? We can use other spectral shape, for instance, like this. It is, right? Because this is, I mean, why is related? Because we will see when we write the completeness. Okay, you see that this is proportional to the number of galaxies, so to the number of sources that you have inside the volume. Okay, we will see that. So when we write the completeness correction. not really the completeness correction, but the selection bias. Yes, please. It can be done, but with one event. So our knowledge about the distribution of the masses of the neutron stars is very, very, very poor. Okay, that's true. You can combine, yes, that's a nice point. So you can combine other information on the neutron stars, yes. As far as I know, probably not. I'm not sure, but probably not. Yeah. Okay, how much time do I have? Okay. Okay, I try to be fast. Okay. So where this information of H naught comes from, okay? To learn how to extract, to make inference, you need to rely on Bayesian analysis, okay? So Bayesian analysis, the heart of the Bayesian analysis is the Bayes theorem, okay? The Bayes theorem is relating my likelihood, okay, to the posterior distribution through a wonderful. I don't need to rush. Okay. So the posterior distribution of my parameter given the data and information on the model is related to the likelihood, this cal L here, that is the probability of observing some data given some parameters, okay, through the prior, that is essentially telling me what my previous understanding of the parameters given the model, okay, our knowledge, our previous knowledge, okay, and normalized to what is called the evidence. Okay? So the likelihood, that is the most important object that we need to understand, is essentially a measurement of probability, okay, to produce some data, this x in the brackets here, that you have observed given your signal. That depends from by some parameters here. Okay? So as I was saying, the guy that we are interested in is the posterior, okay? That is a kind of updated probability of these parameters, because what I want to know are, for instance, in our case, is H naught, that is a parameter given the data that I receive. Okay? The most simple case is a Gaussian likelihood, that you can imagine that, so you have a Gaussian distribution, and this gives the probability of obtaining a kind of data samples given, for instance, the mean and the variance of this object, okay? So this is a simple application, for instance, to extract how the mean and the variance impact on the Gaussian likelihood. Okay, so keep remember this Bayes theorem, because this will be crucial for the determination of H naught. So Costantino will discuss most probably this term here, the evidence, which ratio for two kind of models will be very useful to do a model comparison, okay? So for the moment, I will not discuss the implication of the evidence. So, but what I want to do now is to show you, I don't know if you have already seen, the likelihood for the three different methods, okay? So we will see the likelihood in the dark silence method, the likelihood for the bright silence method, and the likelihood for the spectral silence method, okay? So, and we will see what differentiate these three methods, okay? Let's start from a very simple explanation and the introduction of the likelihood, but let's remember a crucial point. We are trying to inference, okay, parameters that are both parameters of the source, okay? Both parameters of the source, so what are called astrophysical parameters, and also cosmological parameters, okay? So, and this is an extra complication, because I'm not doing inference only on astrophysical parameters, but I'm jointly combine cosmology and astrophysics. People have realized in the past that the famous useful likelihood to approach this kind of problem is called a hierarchical likelihood, in the sense that when I perform my sampling, so I hierarchically, okay, explore the parameter space jointly for the astrophysical and cosmological parameters, and I have to set a hierarchy for my parameters. Okay. Okay, but let's focus on our game, okay, the determination of the Hubble constant. So if you want to start very basic, so you can think about to the probability of generating a binary with parameter theta given some a set of parameters, okay? Again, so here I have my probability, okay? That depends on the parameters, okay? Given the parameters, okay? And I have some parameters on my binary. So this will be equal to the essentially proportional to the ratio between the observation time of my detector over the total number of objects that there are in the universe times the differential number of sources, okay, that I have per binary parameters and detector time, okay? So remember this because this gives me essentially the physical rate of production of binary black holes or other objects, okay? This is the physical rate. Okay, good. So then what is the probability of having a population of sources, of GW sources, with some parameters theta, okay? So if I treat them separately, the total probability of my population will be the product of the single probability normalized to the total one that is marginalized over the parameter, okay? This is a normalization factor, okay? So something that has been mentioned is that so we cannot detect all the sources. This would be great. So, but we have some limitation in the sensitivity, and this brings the concept of selection bias. Okay, that must be accounted because essentially it reduced, if you want, the probability of detecting some events. Okay. So if you build in the future your wonderful detector that will be able to detect all the sources in the universe, okay, you don't have to worry about this guy here. So take this and you normalize, you keep into account the selection bias, okay? There are many papers by Mastro Giovanni discussing this selection bias very carefully, okay? So I refer to them to more details. But the final probability for observing this population of gravitational waves events is essentially a product of the single probability that takes into account normalized by the selection bias. Okay, so if I have my probability, okay, I take into account also my likelihood, okay, for a single event, and then I can convert this and I can write my posterior probability, okay, of XA given the parameter lambda, okay? I essentially added the information from the likelihood. So now the final game is how this likelihood changes for the different methods, okay? So I take my events, I assume that they are, for simplicity, they are independent, okay? And I write my hierarchical likelihood as a product of all these probability distribution, okay? So and finally, the likelihood in general will be this product here, okay? Remember that I treat them separately and I add this normalization factor. Okay, so typically I don't like to be, I like to be, how to say, to translate in physical object, in physical quantity. So then this means that we have to take our likelihood and we have to take into account the fact that we have a finite number of objects, that these objects merge, okay? We have a rate of objects. So I rewrite my likelihood in terms of the physical rates. So I am lazy, so I assume that this is in constant in time, okay? So, and I see that my likelihood gets multiplied by a factor here that is proportional to the number of detection, and we will see what they are, but you can understand is the integration of the rates of events that I have, okay? Given a given threshold of detection times observation times for the integral of the likelihood times the rate, okay? So, and this is the famous hierarchical likelihood that is typically employed for gravitational waves cosmology, okay? Not complicated. So, let's see how this likelihood here changes for the three different types of sources, because you see here there are many dependencies, okay? Let's see how this changes for the three methods that we have discussed so far, okay? Let's try to understand. So I start from the spectral silence, okay? In this case, I know that the detector frame merger rate, okay, becomes this, okay, because I have to take into account the fact that the universe is expanding, and I have to account that the fact that these sources are far, okay? So if you want to move from the detector frame to the source frame, so we have to take into account all the quantity that we have discussed before. So essentially, so this probably is a bit reductive, but the three different likelihoods differs from changing this term here, okay? So if you change these terms here, okay, you parameterize in a different way this source frame rate, okay, you essentially are able to describe the three methods that we have seen so far. So let's start from the spectral silence case, okay? We already know that the two masses are related, detector frame and source frame, okay? And let's write the terms that I was mentioning, okay? Keep into account that I have a finite volume that I am observing, okay? And let's rewrite it in this way, okay? Let's try to understand what are these different quantities. So of course, if you have a rate, you need to have a merger rate for sure, some things that Tanya discussed yesterday, that is R, okay? The number of events that you have per year per gigaparsec cube in your volume. Then you multiply this merger rate by what Tanya mentioned, that was the star formation rate. Let's assume that since we go to high redshift, we take a Maddow-Dickinson star formation rate, and the binary tracks the star formation rate by Maddow. And then you have to multiply by a distribution probability of our masses, okay? And this is essentially the quantity that keeps into account the astrophysical properties of my object, okay? And I assume, as I was saying before, that the mass distribution is independent on redshift. And finally, let's keep into account that we are looking to a finite co-moving volume, so I need to convert this in a physical quantity, okay? So the idea is very simple, okay? And probably we already discussed, okay? So if we have an independent knowledge of the typical source of masses in binary black holes, okay? We assume that they are all formed with primary mass of 35 solar masses, and we use the spectral dependence, and in particular this Gaussian peak, okay, as a standard ruler, okay? And this allows to infer the redshift statistically, okay? So we have the redshift, we have the luminosity distance, we can infer the cosmic expansion. Let's see how we do in practice, okay? So if you take the previous likelihood, you see that you have to compute two integrals, okay? There is one integral over the parameters of the events that have been detected, and then there is an integral to calculate the number of expected events, okay? So the integral over the events, okay, is essentially, how to say, converted from an integral to a Monte Carlo sum, okay, where essentially you sum over all the samples times the prior of the sample times the rate, okay, and you compute the number of injected events simply summing on all the number of injected generated events, okay. So this will be at the end the number of expected events, and this will be the integral that we have to perform on the likelihood, okay. So if you do this job, and people have done for the gravitational waves data from GWTC3, okay, then you write your posterior distribution for H0, okay, you perform your hierarchical analysis, and what you get is this posterior here, okay. This is the posterior obtained from GWTC3 data. Let's look more in details to this posterior, okay. So you see that here we have the posterior distribution on H0 given the data for different kind of mass function. So we have the broken power law, the power law plus peak, and we have the truncated one. So you see that as expected, since these rely on the mass distribution, the posterior changes, okay? I see that with truncated, I obtain something that is 69 plus or minus plus 20 minus 8 kilometers per second per megaparsec. So with the power law, I get something 68, okay? And with the broken power law, I also obtain something 68 plus or minus order 10 events. So I like to mention, I have to stress that it's true that we obtain a posterior, but we obtain a posterior with order 10 error bar, okay? So, and if you compare the spread of this posterior with CMB measurement or with the Schu's measurement of supernova, you see that they are still very broad, okay? And there is another stuff to realize, is that this posterior is not symmetric, okay? But I leave you this asymmetry to you to think about during lunch, okay? And I will ask you in the afternoon why this posterior looks so like that, okay? So very good determination, but still the error are not comparable with determination from other measurements. We have to work more on this, okay? But still, people has computed ratio between models and have computed the bias factor and have looked at which of these model is preferred, okay? But let's see at the drawback or the caveat, if you want, for these methods, okay? So, has been already mentioned that the choice of the peak, okay, impacts a lot on the posterior distribution. And here you can see that if you rerun the analysis, slightly changes the position of the peak, so the posterior goes wherever you want, okay? So you have to be careful, or you have to add extra information in order to get the right posterior. So these posterior are very sensible to the assumption that you do on the masses and on the posterior distribution for the masses, okay? So, of course, so you need to inject some assumption, but you have to be careful when you obtain a posterior for spectral silence that is very sensible to this mass distribution, okay? So, since we have seen the spectral silence, let's now move to the likelihood for the dark silence. That is something that has been asked, okay? Now, I don't rely only on information from the galaxy, from the gravitational waves. I want to add also information from the galaxies. Let's see how I add this in my Bayesian analysis, okay? So, as you can imagine, the math is quite similar to the previous example, okay? So I assume that I have a number of galaxy, number density of galaxies that they are distributed according to some posterior distribution, okay? So the point is that now I need to parameterize my merger rate, okay, as a function of the galaxy catalog, because now I am injecting an extra information from the galaxy catalog, and I want to use the information from the galaxy catalog, okay? So I do some assumption that all the mergers happens inside galaxies, and then that the number of mergers per galaxies are related to some galaxy properties, okay? The second in particular is a strong assumption that we have studied a few months ago, and we have seen that this galaxy property also impact a lot on the inference on H0, okay? But let's be simplistic, and let's assume that this is true, okay? So the number of objects per gigaparsec cube per year will be simply related to the number of mergers that you have in the galaxies, okay? And then you can write your source frame number of objects in terms of the CBC merger rate times the galaxy's merger rate, okay? And so you see, we have introduced the dependence on the galaxies in the term that I was mentioning at the beginning, that is the only terms that distinguish the different approach, okay? So how I parameterize this CBC term, this rate, sorry, okay? I parameterize again in terms of a merger rate, local merger rate, times something that has to take into account the property of the galaxies, that is this function psi, that is models how the rate of CBC per galaxies evolves with redshift and magnitude, and this is the assumption that I was referring to, okay? So I assume that this distribution here is the product, that is a strong assumption between the usual merger rate, okay, times this function here that for me is magic, okay, that is telling me how a gravitational wave's hosting probability is proportional to the galaxy intrinsic luminosity, okay? So take it for true. This is what they use in the LIGO Virgo analysis. If you want to work on this, I'm very happy because I'm trying to understand this more in details. But again, I have a parameterization for my merger rate and from this function here, okay? So now it happens that I have to consider also the fact that I see some galaxies, okay, but I also don't see some galaxies, okay. So I divide my catalog, if you want, in galaxies that can be detected and galaxies that cannot be detected. That enters in what I was mentioning before, that is the completeness correction, okay. So I take into account the two, okay, and I write I try to parameterize my completeness correction, because I know from cosmological other observation that these missing galaxies will be proportional to the Schechter function, okay, the Press-Schechter function that is describing how to essentially the number of galaxies behaves as a function of the magnitude, okay? I use the Schechter function, I cut my galaxies using this theta function, okay? So this means that I cannot observe object when the absolute magnitude is fainter than a given threshold, and I write my physical rate, okay? So of course, if the galaxy catalog is complete, so you don't miss any galaxies, so these terms cancel out, so you have only the galaxy term. Very good. So let's try to write the likelihood, okay? So here, so the rate, if you plug inside all the quantity that we have discussed, we'll have a term that is proportional to the sky position, is a delta in the sky position, okay? And the term with the redshift times this function psi that I was discussing before. So then we work in a simplified assumption, okay? And the physical rate will be the rate of galaxies times all the information, let's say position information that I have in my galaxy catalog, okay? So very good. So I can write my probability population term, and this will be simply this quantity here, okay? So then my likelihood for the dark science will be the likelihood that I've discussing so far over this term here that of course keeps into account that we have selection effect. So if you do, this was something that I was discussing before, okay? For well-localized gravitational events, okay, the hierarchical likelihood can be computed by evaluating the gravitational wave likelihood, okay, or posterior in luminosity distance sky location with the reported redshift and sky position of the galaxies, okay? But if you know that the probability detection of gravitational waves change with the Hubble constant, more and more galaxies will be in as long as we have farther or larger luminosity distance. So since we are in a volume, okay, of a sphere, so this number of detection, the number of galaxies, will be proportional to the cube of the Hubble parameter, okay? So then my likelihood finally, will be this one, numerator over H0 cube, okay? So this is the most simple hierarchical form. I have done many simplification, but this is a likelihood that allows me to get this other posterior distribution using dark science, okay? No electromagnetic information, non-spectral science, okay? GWTC3 allows me to get this posterior distribution. So if you see, here we selected the K-band, okay? That is a particular band of choice, a particular band for the luminosity of the galaxies, and I choose a mass model, okay? So the main point here is that, again, the posterior distribution depends on the band, so on the luminosity of the galaxy that I'm assuming. But the other point that I want to stress is that still we have error bar of order 10, okay? Unfortunately, even dark science does not allow me to shrink the error bar, okay? So finally, okay, also you can imagine that the population property also impacts the posterior distribution, and also the variation of the galaxy catalog parameters also have an impact on the posterior distribution. So I don't have much time because I want to use the final time to describe a bit dark energy, okay? What I want to do, just in 1 minute, is that if you want to write the likelihood for the bright sirens, okay, you don't have to go crazy. So you multiply your likelihood for the gravitational waves times the likelihood for the electromagnetic events, okay? Okay, you do some assumption, I arrive at the end, but the final likelihood, okay, in the simplified case, if you want, is this quantity here. The convolution of the likelihood of the gravitational waves times the likelihood of the electromagnetic events over, again, this correction factor given by the the selection bias. There is a big advantage is that the likelihood for the electromagnetic event are 2 delta. Okay, it's the product of 2 delta, because I know very well where this guy here, both in redshift and in the position space. So, and this simplifies a lot my final likelihood. Okay. So I do the Bayesian inference, and I get this posterior here. Okay, this is the posterior with 0817. Okay, from one single event. So you see that we get a posterior distribution for H naught. So we compare this posterior distribution with from the gravitational waves events, from the Planck determination, and from the Schur's determination. You see that we have an order of magnitude larger error, but we are there. Okay. So then people have reanalyzed this likelihood, adding other information, for instance, adding radio band information, and you see that in this case the posterior shrinks a lot compared to the just gravitational waves determination alone. So this means that extra information can help us. So this table summarizes the pros and cons of the different likelihood. The main point that I want to stress is that unfortunately, okay, so the error scales like 1 over square root of n. So since we have a limited number of events, you can already understand that we are not comparable with the determination from CMB measurement or cosmic distance ladder, because you see our error band is much, much larger. But imagine that in the O4 catalog, you have 15 events, bright silence events, okay? So you see that the error band starts to become very interesting, okay, just with 15 bright silence, okay? That is the reason why there is a lot of interesting science for gravitational waves for cosmological parameters. So now the question is that how do I improve this measurement? Please, you have a solution. So you reply to 2 questions with this answer. Okay. The first one is that you understand why this posterior has this shape. Okay, this is exactly the degeneracy between dl and iota. This is the inclination angle. Okay, so if you have extra sources like electromagnetic sources to break this degeneracy, you improve the determination. Okay, and the fact that dl and iota are degenerate in the waveform, something that I didn't discuss at the beginning because I was checking if you were awake. Okay, so it's the reason why. So you improve it. You rely on external electromagnetic observation. Yes, absolutely. So what we are developing, for instance, in PISA is a code that does this electromagnetic identification as fast as possible. We call it SkyFast. And this will be exactly this point, that arrived my events, that triggers, I didn't explain how it works, but probably has been explained by Zoltman, right? So the gravitational events comes, this trigger, okay, our code in the same way as Biostar does, okay? We send a circular to all the electromagnetic facilities, okay? And they move their telescope in that direction, okay? And they try to do the identification. What we are adding compared to Biostar is that we add the information on the inclination angles that is crucial for also for selecting the kind of electromagnetic counterpart and the kind of sources that you are looking at, because you would expect a different inclination angle. For instance, in the, I didn't discuss this, but in the gamma ray burst case, that is very important because it's telling me some information on the kind of sources. Absolutely. I will still 5 minutes from the. Please, please. No, go ahead. No, sorry. Okay. ISR does not include inclination angle at the moment. They are working. I know that they are working on that, but at the moment it's not. it's not the only thing. So you can also add some other extra information or use more refined waveforms. So if you include precession or if you include higher modes, you can break better this degeneracy. But if you rely on electromagnetic stuff, so without using more advanced waveforms that help on one side but complicate the analysis because you have to run your analysis on other parameters. So the addition of other extra electromagnetic counterpart will help to break this degeneracy. Please. The table. Exactly. You have to assume a mass distribution that can change. You can do reverse engineering. Yes, this is what you mentioned. Yes, you fix these and you infer the others. You can do that. Absolutely, good point. I think that people have done this, right? So I'm not sure, but I read something. So you can do the opposite. That's a very good point. Yeah. Okay. So I will not discuss third generation detectors because I don't have time. So we will see each other in the next school. Okay. But one way to improve this measurement is go deeper in sensitivity and or going lower in frequency. Okay. Uliana can tell you more about if you go deeper in sensitivity. So you go towards the building of Einstein telescope or cosmic explorer, what we gain. Okay. So Uliana has put a lot of efforts in these studies, okay? So mainly focus on ET, okay, in its different configuration. So the only things that you have to remember, okay, is not the only, but one of the most important things is that we are looking at the universe that is next to the corner with second generation detectors. The ability of third generation detectors is that they will allow us to look for in some region where we are really far and we can learn a lot of cosmology and astrophysics, okay? So something like, so I put here redshift 50 because Punturo like to push a lot toward, but we will not reach redshift 50, okay? Realistically speaking, we will go at redshift 30, something like that, but there are other problems coming into play, okay? But the only things that I want to highlight is that. Okay, third generation detector, okay, ask Juliana, and you will see that with order 1 million of event per year, you shrink your error bar on H0 of order of few percent, okay, less than % level, okay. So this means that third generation detectors will really allow to put constraint on the H0 parameters at the level of CMB or other ladder, okay. And gravitational waves becomes the third, I would say, probe to probe, the third way to probe late time cosmology. Okay, so in the last 3 minutes, I want to mention the dark energy possibility. Okay, the dark energy, the way in which we can use gravitational waves to probe dark energy. Okay, it still rely on dark sirens or bright sirens. So it's very easy, the math, okay? Because you don't assume that you have a cosmological constant, so a fixed equation of state, but you allow this parameter omega, okay, to change with redshift, okay? So you perform a parameterization, okay, and this parameter, omega dE, dark energy, is describing your behavior of dark energy at high redshift, okay? So this means that your luminosity distance is not anymore the ones that I presented so far, but changes with the dark energy term here that depends on redshift. It's not a constant anymore. So you do a parameterization, you assume a parameterization that has become very popular in the recent year, in the recent months, thanks also to DESI analysis of large-scale structure, okay? So, and you try to infer omega 0 and omega A, okay? So if you trust in the cosmological constant, so then you know that omega A, okay, is 0 and omega 0 is equal to -1. But if you don't trust in the cosmological constant, then you run the analysis, you combine the analysis, for instance, with the electromagnetic observation, so and then you see that the uncertainty that I can get on omega 0, omega 8, and omega A are very informative, okay? So you see that gravitational waves with ET, this is the case of ET in different configuration, can also probe dark energy evolution, okay? And this is another interesting application, how to use gravitational waves to probe dark energy. Final topic, so in a similar way, gravitational waves feels the fact that they travel in a modified gravity framework, okay? So we have seen yesterday that the evolution of gravitational waves in GR is essentially telling us that this guy redshift is similar to radiation, okay? And this scale factor scales like the luminosity distance, okay? But if you are in a modified gravity setup, then there is an extra friction there, this alpha m, okay, that modifies the propagation of gravitational waves. So instead of using standard luminosity distance, I define this new luminosity distance that people have called luminosity distance for gravitational waves, okay? So if you think that we live in a modified gravity setup, then these two will be different, okay? The luminosity distance from gravitational waves and the one from electromagnetic emission will be different, and we parameterize in this way, okay? Where this parameter is essentially keeping into account that the universe is modified, okay? Is modified gravity. So again, you use a parameterization for this difference, okay? So if these two will be the same, you will find xi 0 equal to 1. So if this is different from 1, then you will find that this, of course, has an evolution with the redshift, okay? So you take these two parameters, xi 0 and n, okay? And you use the LIGO-Virgo data, okay? And you see that there is the possibility already with GWTC3, okay, to test the fact that we live in a modified gravity universe or not, okay? So if you want to go further, okay, and you also to have a more stringent constraint, so you simulate your data for ET, okay, and you run the analysis for this parameter n versus 0, okay? So, and this is another interesting way to test, to see how gravitational waves can be used to test modified gravity, okay? And this is an extension adding an electromagnetic counterpart. So we'll not discuss LISA, so remember that we go higher in redshift and we have other sources, but the math is the same, okay? Let me conclude, okay? Because I'm already late. So I hope that, so we cover two huge topics. So we cover the early universe and the late universe. So I decided to do this choice. It was a bit, let's say, could sound a bit too much information. I hope that you get the main idea, okay, of the early universe application of gravitational waves and the late universe application of gravitational waves. So in this slide here, so is a summary of the late universe point that I learned measuring gravitational waves from resolved sources. What the only point that I like to stress is this, okay? So people have built gravitational wave detectors having in mind astrophysics. In reality, if you think about Virgo, this was built for supernova detection, okay? Now, in the past years, we realized that astrophysics is not the only implication that we have. We have a lot of implication for fundamental physics and for cosmology. And I think that you will be the future to understand even more and even more in details and with more accuracy how we can use gravitational waves, okay? So at least you have an introduction to this. This was just a simple introduction, but I hope that you enjoy, okay? And feel free to ask me questions, okay? And then we stop here.